We look at that little dot on our maps all the time, the one telling us exactly where we are. It feels so simple, right? But what if I told you that behind that dot is a constant, high-stakes physics experiment, one that proves every single second that Albert Einstein was a genius? And it all starts with one pretty shocking number.
11 kilometers. That's nearly 7 miles. I mean, imagine your phone telling you that you're at work when you're actually halfway across town. That's a pretty big difference, wouldn't you say?
Well, get this. That 11 kilometers is how far off your GPS would be after just one day if we didn't account for Einstein's theories of relativity. So the real question is, how does a 100-year-old theory about the very fabric of space-time keep our modern navigation system from being completely useless? All right, so to really get how Einstein is the hero of this story, we've got to start with the basics. The simple, elegant geometry that most of us think is the whole story. The whole system is built on this idea called trilateration. The easiest way to think about it is like a giant geometry problem happening in the sky. Your phone isn't measuring angles or anything complicated like that. It's just asking one simple question over and over. How far am I from that satellite? So let's break that down. Imagine one satellite sends out a signal. It tells your phone you're, say, 20,000 kilometers away from it. Now, that doesn't pinpoint you. It just means you're somewhere on a giant invisible sphere with that satellite at the center. Okay, now add a second satellite. Where two spheres intersect, you get a circle. So now you're somewhere on that circle. A third satellite narrows it down even more to just two possible points. And that fourth satellite, that's the magic bullet. It confirms which of those 2 points is you. And this is the really crucial part, it helps solve for time itself. This picture makes it way easier to visualize, right? In 2 dimensions, like on a flat piece of paper, you just need 3 circles. And bam, they cross at a single point. But since we live in a 3D world, we're using spheres instead of circles. And that's exactly why we need that fourth satellite to nail down our precise location in 3-dimensional space plus time. Seems pretty straightforward, yeah? Well, about that. It turns out this whole beautiful, elegant geometry puzzle completely falls apart unless one critical thing is almost impossibly perfect. And that thing is time. And this is where it gets absolutely mind-boggling. See, to figure out distance, your phone multiplies the signal's travel time by the speed of light. Now, if you want that distance to be accurate to within a single meter, your timing has to be correct to within a few nanoseconds. We're talking a few billionths of a second. That kind of precision is just wild. It's the reason every single GPS satellite has multiple ultra-stable atomic clocks on board. But even with perfect clocks, there's another snag. That signal's journey from space to your phone isn't a clean shot through a vacuum. No, it has to punch through our atmosphere, bounce off buildings, and deal with all sorts of real-world messiness. So the engineers who built this system had to account for a whole laundry list of potential errors. You've got tiny miscalculations in the satellite's exact orbit, little drifts in the clocks themselves, and really big delays when the signal travels through the Earth's atmosphere. Then you add in signals bouncing off skyscrapers, and even tiny errors inside your phone, and, well, you can see how all these little inaccuracies start to stack up. And this is what that looks like in reality. Your actual position isn't one perfect, clean dot. It's more like the center of a fuzzy cloud of possibilities. The entire job of the GPS system is to constantly correct for all those errors to make that cloud as small and as tight as humanly possible. This table gives you a rough idea of where those errors come from. For you and me, the biggest troublemaker is the ionosphere, which can throw things off by about 4 meters. But look at these numbers. None of them are huge, and they definitely don't add up to that 11-kilometer disaster we talked about at the beginning. So what gives? Where is that massive error hiding? And that brings us to the biggest source of error of them all. But here's the twist. It's not really an error at all. It's a fundamental feature of how our universe works. This is where Einstein's theories ride in and save the whole system from total collapse. Okay, so there are 2 of Einstein's big ideas at play here, and they're actually fighting each other. First, you've got special relativity. It says that the faster something moves, the slower time passes for it. Since those satellites are screaming through orbit, their clocks actually tick a tiny bit slower than ours. But then you have general relativity, which says gravity warps time. The weaker the gravity, the faster time ticks. The satellites are way up high where gravity is much weaker, so their clocks actually run faster than ours. Let's put some numbers on that. Because of their incredible speed, that's special relativity, the satellite clocks lose about 7 microseconds every day. That's 7 millionths of a second. It's tiny. But because they're in a weaker gravitational field, that's general relativity, they gain about 45 microseconds every day. So the gravity effect is actually way more powerful than the speed effect. So you do the math. A gain of 45, a loss of 7, and the net result is that every satellite's clock gets ahead of a clock on Earth by about 38 microseconds a day. Now, 38 millions of a second sounds like absolutely nothing, but when your entire system is based on the speed of light, that tiny time gap blows up into a massive distance error. And there it is. That's our 11 kilometers, piling up day after day. So, how in the world does the system deal with this? It's because GPS was designed from the ground up to be a massive, constantly self-correcting physics machine. It all comes down to how the different parts work together. You can think of it in 3 parts. You've got the space segment, that's the constellation of satellites. You've got the user segment, that's your phone or the GPS in your car. And then you have the real nerve center, the control segment. This is a global network of ground stations that do nothing but monitor the satellites, 24/7. These ground stations are constantly calculating the exact orbit of every satellite and measuring precisely how much its clock is drifting, and yes, that includes those predictable effects from relativity. They package all of that correction data together, upload it to the satellites, and then the satellites broadcast it down to your phone, along with everything else. It's a constant, never-ending feedback loop. And here's the coolest part. The engineers knew this would happen. So before a satellite even leaves the ground, its clock is intentionally built to run just a little bit slow, because they're anticipating the net effect of relativity once it gets into orbit. I mean, how incredible is that? That satellite flying over your head isn't just a fancy radio. It's a physics laboratory running a continuous, real-world test of Einstein's theories. So the next time you look at that little blue dot on your screen, remember what you're really seeing. It's not just your location. It's hard proof that time runs differently in space than it does here on Earth. It is the daily, silent confirmation of one of the most profound theories in science, all working perfectly just to get you where you need to go. And it really makes you wonder, doesn't it? What other amazing marvels are just hiding in plain sight, woven into the technology we take for granted every day?